Hello. Uh, there might be some. Okay. Now, hello and welcome to our sixth lecture of the webinar series conducted by JIS Institute of Advanced Studies and Research, Kolkata. For the attendees who have registered for the first time in this series of lecture, let me first begin with the brief overview of our institute. So JIS Institute of Advanced Studies and Research, in short, it is JIS IASR, Kolkata. This newly formed institute was established about 1 year ago as a constituent of JIS University under the flagship of JIS. The prime objective of our institute is to conduct the translational research and to promote the translational research in the field of computer science, health science and technology, and interdisciplinary sciences that includes material science, polymer, and sensor technology. So presently, we are offering mainly postgraduate courses as well as PhD on the above areas. So this institute is growing since its inception under the leadership of our director, Padma Shri Professor Ajay Kumar Ray. We have a strong group of exceptionally talented and experienced faculty members in our institute. So on behalf of our institute, I would briefly inform to all the attendees that the admission to several postgraduate courses is now open, and I will share you the details, brief details of these different courses. So let me share the, yeah. You can see the slides where the different postgraduate courses are there, and we are offering these courses on like MTech in computer science and engineering with specialization in data science, MTech in computer science and engineering with specialization in machine learning. We also are offering MTech in sensor technology and IoT, MTech in bioinformatics, MSc in polymer science and technology with specialization in paint and coating, and also MSc in medical biotechnology and bioinformatics. So other than that, let me tell you that other than that, we are also offering different 3 years executive MTech courses for working professional. And you can find all the details of these courses in our website, or you can visit our Facebook page, or you can send your queries through email to us. Like email is admission@JISIASR.org, or the phone numbers are given. You can call us on this phone number. Okay, now I would like to welcome our today's speaker, Dr. Biplab Paul. I know Dr. Paul for last 12 years since my PhD time in IIT Kharagpur. The old and gold days were there, and he was my senior at that time in my PhD. So Dr. Paul is now working as an assistant professor in thin film physics division at Linkoping University, Sweden. He is an expert in thermoelectric materials and device design and fabrication. His research interests include thin film synthesis for energy, electronic, and coating applications. In Sweden, Dr. Paul has initiated a new research line in flexible thermoelectrics to power wearable electronics from body heat. His long-term research goal is to find the alternative environment-friendly power solutions contributing to the development of carbon-free economy. So before I invite Dr. Paul for his talk, just to inform all the attendees that they can ask their questions, if any, by writing it in the section called Q&A in their device, and our speaker will answer those questions at the end of his talk. And also for your information, I would like to say that this webinar, you can see the webinar live in our institute official Facebook page at www.facebook.com/JIASR. So now I would now leave this platform for our speaker, Dr. Biplab Paul, to present his talk for this webinar on scope of thermoelectrics as potential energy resource. So it's over to you, Biplab.
Thank you, Dr. Bosenjit Shah, for this nice introduction. So I'll try my best in next 45 minutes. Um, so I'm sharing the slide. Okay. So I will talk about scope of thermoelectrics as a potential renewable energy source. So this is an introductory lecture on thermoelectrics for broad audience. Those who want to go more details, follow the references in reference list. So outline of my talk is, first I will give a general introduction on thermoelectrics. Then I will discuss different thermoelectric effects. Then I will come to the how we can use thermoelectrics for different purposes. After that, I will discuss about different limitations on thermoelectric efficiency. Then I will come to the discussion how we can overcome those limitations for higher thermoelectric efficiency. And finally, I will end with the discussion about emerging areas of applications. So here, thermoelectric is compared with two other power sources, hydraulic power and battery. So what happens in hydraulic power? In hydraulic power, gravitational potential is the driving force. So due to gravitation, water flows down, rotate turbines, and power generated. In battery, electric potential is the driving force. In thermoelectrics, temperature gradient is the driving force. So due to the temperature gradient, charge carriers move from hot side to the cold side and take part in transport process, and thus power generated. So this slide shows schematical diagram of a thermoelectric.
Just a minute, Biplab, just to
Yeah.
interrupt. Can you enlarge this slide so that it can be seen?
One
Can
minute.
it be enlarged? Full screen kind of thing?
Full screen.
In the bottom, you can have this one, I think. Is it possible? Then otherwise...
I don't find any option.
Okay, then it will be... If there is no option, then you can continue. Yeah.
1 minute.
Yes, please continue. No issue.
Display setting. I don't find any option to, sorry.
It's okay, it's okay.
Okay, fine. So now we try to understand how thermoelectric device works. So each thermoelectric device consists of many thermocouples, and each thermocouple consists of N and P type legs. So thermocouples are connected in series electrically and in parallel thermally. So what happens here? Electron and holes from hot sides moves to the cold sides and passing through the load again come to the hot side. So these cycles goes on and this power generated. So thermoelectric performance any device depends on three parameters: Seebeck coefficient, electrical conductivity, and thermal conductivity. So for high output power, electrical conductivity of active thermoelectric materials should be high. Seebeck coefficient should also be high for high output voltage. What is Seebeck coefficient? Seebeck coefficient is the voltage developed across a specimen due to unit temperature gradient. I will discuss more about Seebeck coefficient later. Also, output voltage depends on the temperature difference across the module. So for high delta T, thermal conductivity of the active materials should be as low as possible. So thermal conductivity consists of electronic contribution to thermal conductivity and lattice contribution to thermal conductivity. That means charge carriers conduct some heat, as well as phonon or lattice vibrations also uh, take part in conduction process of heat. So we don't have much scope to play with the electronic contribution to thermal conductivity, because you can spoil the electrical conductivity also, but you definitely play with the lattice contribution to thermal conductivity. So thermoelectric materials are called phonon glass and electron crystal. Why? Those materials act as glass to phonon and act as crystal to electron. This slide shows the emerging area of applications for thermoelectrics. Thermoelectric is important for waste heat recovery. In different applications, 66% of energy is wasted as heat. Recovery of even small fraction of this wasted heat into electrical power can have huge impact on energy economy and environment. So I'll discuss about different thermoelectric effects. First come to the Seebeck effect. So it was discovered by Thomas Johann Seebeck in 1821. So when a temperature difference is created between the junction of two dissimilar metals, some voltage is generated, and that voltage depends on Seebeck coefficient of metal A and Seebeck coefficient of metal B, and also the temperature difference between the junction. So now we will try to understand more about Seebeck coefficient, what Seebeck coefficient actually is. If you take a piece of conductor, for example, metal, its charge carriers mainly electrons. When it is subjected to a temperature gradient, electrons from hot side move to the cold side. Some atoms at the cold hot end left ionized, and cold end is accumulated with negatively charged electrons. So that's why voltage developed. And Seebeck coefficient is the ratio of developed voltage to the applied temperature gradient across the conductor. Now I'm coming to the Peltier effect. Peltier effect, just reverse of the Seebeck effect. When you pass current through this loop of two different metals, heat is generated at one end and other junction is cooled. If I is the current through this loop and Q is the rate of heating or cooling, Peltier coefficient is defined as the ratio of Q and I. Seebeck effect and Peltier effect are closely related, first understood in 1855 by William Thomson. And this expression shows how they are related. There is other effect called Thompson effect. This is reversible heating or cooling when there is both electric current and temperature gradient. In other way, you can say current flow through a temperature gradient across a specimen will generate and absorb heat depending on the Thomson coefficient, either positive or negative value. So all thermoelectric effects are reversible effects, but any thermoelectric operation always encountered with irreversible effect. that is joule heating, that is killing for thermoelectric efficiency. When the contact resistance between the metal and semiconductor in thermoelectric device is high, joule heating effect can be detrimental for thermoelectric efficiency. So special care need to be taken when make contact in real modules. Now I am coming to the Kelvin relations. So any thermoelectric operation involves both heat flux and current flux, that is electronic and photonic transfer are coupled. So heat flux, current flux can be represented as a function of electric potential and temperature gradient. Same with the heat flux by this equation. And finally, heat flux and current flux are related through this matrix equation. Before I discussed about Seebeck coefficient, what is Seebeck coefficient? Now we try to understand physically what is the physical meaning of thermopower. So we take that equation for heat flux density. When temperature gradient is 0, then heat flux can be is equal to the Seebeck coefficient times absolute temperature times current density. From that we get this expression. This is actually entropy current density and this is electric current density. So thermopower or Seebeck coefficient is the ratio of the entropy current to the electric current. That is, you can say entropy per carrier. That means energy carried by each charge carriers is the Seebeck coefficient. Now I will discuss how we can use them. Most popular use of thermoelectrics is the use of thermocouples as temperature sensors. So depending on the metal A and metal B, thermocouples can be of different types for different temperature applications. As I already discussed about the Peltier effect, thermoelectric device can be used as a refrigerator by exploiting the Peltier effect. It can be used as thermoelectric generator by exploiting Seebeck effect. Now I'm coming to some existing application. The most successful use of thermoelectrics is done in space applications where there is reliability is more important than efficiency. For example, NASA is using in their space mission that lab rover Curiosity was sent by NASA in Mars was powered by radioisotope thermoelectric generator. What is radioisotope thermoelectric generator? It has one radioactive core that generates it, and surrounding it there are many thermoelectric modules that convert core heat into electrical power. And thermoelectric device is also used for cooling electronics system, for example, cooling imaging system. So why thermoelectric module is used? Because it's offer noiseless operation. It doesn't have any moving parts. So it's only charge carrier moves. So imaging quality of the camera become more high. Thermoelectric device is also used in military vehicles as auxiliary power units. And nowadays, portable thermoelectric cooling system are popular. Those who are going for for a trip outside. Now I will discuss about the limitation of thermoelectric efficiency. Thermoelectric efficiency is expressed by that expression. Here the first term is called Carnot efficiency. Thermoelectric efficiency is equal to the Carnot efficiency when GT is equal to infinity. What is GT? GT is the ratio of power factor and thermal conductivity times absolute temperature. Here S is Seebeck coefficient, sigma is electrical conductivity, kappa is thermal conductivity, and T is the absolute temperature. So Our task is to maximize GT, but we cannot abruptly change all those parameters to increase GT drastically because all those parameters are coupled through solid state transport theory. Seebeck coefficient is inversely proportional to electrical conductivity. When you increase electrical conductivity, Seebeck coefficient decreases. Further, if you increase electrical conductivity, it will increase electronic contribution to thermal conductivity, again deteriorating the thermoelectric figure of merit. So this is a real challenging task to improve GT value. Now, we'll see what is the thermoelectric figure of merit of commercially available thermoelectric materials. It's about near 1. But for thermoelectric to be competitive with other alternative power sources, GT value should be above 2. There are some materials developed in lab with GT value above 2. However, they are not yet commercialized. So now we try to understand which materials is good for thermoelectric application. What do you think about metal? Metal has high Seebeck coefficient, but metal has high electrical conductivity, but it has low Seebeck coefficient and also high thermal conductivity. So finally, metals are poor thermoelectrics. What about insulators? It has high Seebeck coefficient and high or low thermal conductivity depending on the type of material. But definitely all insulators have electrical conductivity near to the 0 value. That means again insulators are poor thermoelectrics. Now we try to understand then what kind of materials should be good for thermoelectrics. So this figure shows the variation of Seebeck coefficient, electrical conductivity and thermal conductivity as a function of carrier concentration. So you can see here carrier concentrations should be optimized within certain range for high thermoelectric figure of merit. And semiconductors or semi-metals are in this range of optimized carrier concentration that provide high thermoelectric figure of merit. That means heavily doped semiconductors are good for thermoelectrics. So semiconductors have sufficient electrical conductivity, high Seebeck coefficient, depending on the, it can be both negative and positive, depending on the what type of conductivity it has. It can have high or low thermal conductivity depending on the material system. So electronic contribution to thermal conductivity can be expressed by Weidmann-Franz law. Here, L is Lorentz number, sigma is electrical conductivity, T is the absolute temperature. That means electronic contribution to thermal conductivity is proportional to electrical conductivity. So what about phonon contribution to thermal conductivity? You know that a phonon is quantum of lattice vibrational energy. It's in analogy to a photon, a quantum of light. In non-metals, phonon thermal conductivity often dominates over electronic contribution to thermal conductivity. For example, in semiconductors, 75% of heat mainly conducted by phonon, whereas in metals is the reverse. Now we will try to understand about the Seebeck coefficient of metal. We know that electrical conductivity of metal is high. What about Seebeck coefficient? So we first assume, let's simplify it. We assume the charge carriers as classical gas particles. So each particle has energy 3/2 times Boltzmann constant times temperature. And by definition, we know that Seebeck coefficient is entropy per carrier. Entropy is the energy divided by temperature. So finally, we get 3/2 times Boltzmann constant. And Seebeck coefficient we get as 129 microvolt per Kelvin for metal. But actually, Seebeck coefficient of metals is one order of magnitude lower than that value. Why this discrepancy? Because we assumed the charge carrier as classical gas particles. Actually, charge carriers inside the crystal are not free to move like gas particles. They move under certain periodic potential, and their behavior is guided by the Fermi Dirac statistics, and this is Fermi distribution. So if we assume the charge carriers is free particle, its energy is a function of momentum and mass. Here P is momentum, M is mass, K is wave number. So we can plot that equi-diagram. So according to classical physics, uh, all the charge carriers should reside in all the levels inside that parabola. However, it is not true when the charge carriers is under uh, some periodic potential. So energy level are quantized, and at 0 Kelvin, all the levels below Fermi energy are occupied by charge carriers. That means there is no charge carriers to take part in transport process. When we heat it up, like that particles in that box, so some particles goes above the surface level and take part in transport process. Similarly, when you heat it up, some carriers goes above the Fermi level and take part in transport process. So charge carriers well below the Fermi level, they don't take part in transport process. So fraction of electrons that take part in transport process is less than 1. And we Seebeck coefficient we obtained as this. This value approaching near to the actual value, however, it is not exact. For exact value, you need to do rigorous theoretical calculation. One approach derivation of semi-classical Boltzmann transport equation. So correct expression depends one factor that is called scattering factor R. I'm not going to discuss in details about that. You can follow the textbook in reference list to have the idea of scattering factor. So we have learned that semiconductors are good for thermoelectric application. But what type of semiconductors? We know about intrinsic semiconductor when there is a number of electrons and holes are same. Lightly doped semiconductor, so it's extrinsic or non-degenerate semiconductor. Fermi level is near the band edge. And heavily doped semiconductors or degenerate semiconductors, here Fermi level goes deep inside the band. In case of intrinsic semiconductor, Seebeck coefficient depends on the contribution from electrons and holes, and they are opposite, and so that's why they cancel each other. That's why Seebeck coefficient of intrinsic semiconductor is very low. In case of non-degenerate semiconductor, it follows that equation. A is a constant here. It involves many parameters, effective mass, scattering factor. I am not discussing that. And in case of degenerate semiconductor, Seebeck coefficient is inversely proportional to the carrier concentration. So with the increase in carrier concentration, Seebeck coefficient decreases. Here MD is the effective mass, KB is the Boltzmann constant, H is Planck constant. Now we try to understand how Seebeck coefficient changes with the variation of carrier concentration. So below 10 to the power 17 per centimeter cube, 2 carrier conduction happens. So that means it's intrinsic semiconductor regime. Above 10 to the power 17 to 10 to the power 19, it follows non-degenerate statistics. Above 10 to the power 19, it follows the degenerate statistics. So thus the nature of the semiconductor changes with the variation of carrier concentration. And we know that heavily doped semiconductor, that means degenerate semiconductors, are good for thermoelectric application. Now I will discuss how to overcome the limitations for higher thermoelectric efficiency. This figure nicely represented how spin, orbital, charge, and lattice contribute to the thermoelectric figure of merit. I don't have scope to discuss the contribution from all. I'll discuss mainly the most popular strategies. You can follow that paper. This is a nice paper. Okay, most popular approach for the enhancement of thermoelectric efficiency is to scatter phonons by the introduction of grain interfaces inside the material system. For that purpose, bulk nanostructured materials are grown. So here, grain boundaries act as potential barrier for charge carriers. So it scatter scatter low energy charge carriers and thus increases average energy of charge carriers, which in turn increase the Seebeck coefficient. Why? By definition, we know that Seebeck coefficient is the entropy per unit charge, entropy per carrier. That means energy per carrier. And here's electrical conductivity is an exponential function of barrier height. And apart from grain interfaces, that nanodots inside the materials also act as scattering center for charge carriers. So nanodots scatter both phonon and charge carriers. Nanodots are helpful to scatter intermediate phonon having from a mean free path of medium range, and grain interfaces scatter phonon with long mean free path. So during my PhD, I studied two different nanocomposites. One is lead telluride bulk nanostructured materials. Other is silver doped bulk nanostructure lead telluride. Here, in silver doped lead telluride, silver forms nanodots within the grains. So in this figure, electrical conductivity as a function of temperature is shown. Bulk lead telluride acts like semi-metals. So Seebeck electrical conductivity, that's why decreases with the increase in temperature. But in nanostructure materials, it's opposite. That Seebeck electrical conductivity increases with the increase in temperature. Why? With the increase in temperature, more and more charge carriers get the energy to cross the barriers and take part in transport process. So it acts like semiconductor. So bulk nanostructuring converts semi-metallic nature to the semiconductor nature. And what happens with Seebeck coefficient and thermal conductivity? Seebeck coefficient increases by 20 to 30%. On the other hand, thermal conductivity decreases by 30 to 40%. Now we will see if GT value enhanced. Unfortunately, no. Why? GT value still remaining near 1 because scattering of charge carriers reduce the mobility of both the samples. In undoped bulk nanostructure lead telluride, mobility is around 349 centimeter square per volt second. And in case of silver doped lead telluride, because of additional scattering from nanodots, mobility reduced to half. So that's why electrical conductivity is drastically deteriorated. So that's why GT value is not increased. So how to scatter phonon without spoiling charge transport? Okay, let's see other case study. So what happens if we introduce nanodots within the material system that has perfectly lattice matching with the host matrix? Yeah, this is helpful to avoid scattering of charge carriers, but this is not sufficient. The band of the nanodot should be perfectly matched with the host matrix. It happens the same here. Conduction band of the nanodot and host matrix perfectly aligned. And that's why mobility of electrons is high, above 1000, which results in high GT value about 1.5 at 650 Kelvin. Now I will discuss about one interesting work, nanostructuring at all scale. That means, so first solid solution, you replace some atoms from the host matrix with lighter atoms like sodium. So due to atomic mass fluctuation, it scatters phonon with low mean free path. When you introduce some nanodots inside the matrix, it scatters phonons having mean free path in the range 10 to 100 nanometers, and that drastically reduces thermal conductivity because the phonons in this range contribute to the 80% conduction of heat. And that's why GT value increased to 1.7. Finally, if you introduce gain interfaces at mesoscale, it scatters phonon with long mean free path, and thus GT value is enhanced to 2.2. Other interesting example for the improvement of thermoelectric efficiency is the convergence of band taking part in transport process. In lead telluride, generally L band take part in transport process, but when it converges with sigma band, so total 12 band takes part in transport process when the bands are converged, which improves the Seebeck coefficient as well as electrical conductivity, and thus thermoelectric figure of merit can be enhanced. Other interesting strategy for the enhancement of thermoelectric efficiency is the enhancement of density of states near Fermi level. To understand that, we have to go through that expression, Mott relation for degenerate statistics. We have two factors here. One factor is related to the mobility, other factor related to the density of states. So if density of states near Fermi level is enhanced, it can improve Seebeck coefficient. So here one example, thallium doped lead telluride. Thallium forms its impurity level inside the valence band of lead telluride, which enhance the density of states near Fermi level, which increases thermoelectric figure of merit drastically. Now I will discuss what are the emerging areas of applications. Thermoelectrics started with the bulk materials, and I already mentioned that the most successful use of thermoelectric was in space mission. But nowadays, many people are focusing on use on Earth, particularly on-chip cooling, that is thermal management of electronic devices. So Micropelt launched a micro thermoelectric cooler based on thin films in 2011. And in 2013, Fujifilm launched organic material based thermoelectric generator, which could generate power milliwatts just from 1 Kelvin temperature difference. But problem with the organic materials is that they are not stable over time. So we need to work on how they become stable. So future demand is development stable, flexible materials for wearable and flexible thermoelectric application. This shows the energy range of different electronic applications. So thin film based micro thermoelectric cooler or generator can be used for low power applications. So this scheme shows different wearable and implantable application. Micro thermoelectric device can be integrated with the smart glass, activity tracker, smartwatch, and it can also be implanted within the body for some biomedical application, for example, to power pacemakers. And I already mentioned that thermoelectric microcooler can be useful for on-chip cooling. So you know that with the decrease of dimension of electronic microsystem, some spot even gets hotter than 50 degree, and removal of heat from that hot spot is important for reliable performance. No other technology other than thermoelectrics is useful for on-spot cooling. So micro thermoelectric cooler is promising for thermal management for electronic devices. This figure compares thermoelectric figure of merit of inorganic films, polymers, and hybrid materials. So inorganic films give the highest figure of merit, but problem with inorganic material is that they are inherently rigid. So to use inorganic materials for flexible applications, some flexibility need to be induced within the material. But in this process, you may spoil the thermoelectric performance of inorganic materials. What we are doing at Linkoping University, we are working exactly in that direction, that we try to induce flexibility in inorganic materials. So we developed fully inorganic flexible thin films to generate power for from extra high temperature or for application in hostile environment. For example, application for fire workers where organic materials cannot sustain high temperature. So that concept was awarded with Best Presentation Award by European Thermoelectric Society in Thermoelectric Conference. And also we working with the wearable thermoelectric application. So we are doing in two ways. One way, transfer the film, inorganic film on organic polymer platform, and other way, make the hybrid film. So body generate almost 100 watt of heat through metabolism. Even the recovery of certain fraction of heat is sufficient to power wearable electronics or biomedical devices. So we developed recently nanoporous film. So here interpore separation is higher than electronic mean free path. So that's why charge transport is not hampered, but it's scatter thermal conductivity drastically. That's why reduce the thermal conductivity one order of magnitude. And other interesting fact of that film is that film is attached to the substrate by nanopillars. So you can easily strip the film and transfer the film on polymer platform just by stripping like perforated paper. You can go through these references for more details. And thank you for your attention. but I can give you some assignment to brainstorm to think about. Assignment 1, you can go through this link and try to play with. You put different values of uh, effective mass, mobility, and try to understand how Seebeck coefficient and electrical conductivity and thermal conductivity changes and improve thermoelectric figure of merit. Assignment 2, you try to understand what happens if there is no phonon contribution to thermal conductivity. There is only electronic contribution. So how you can express GT value? And generally, metals have charge carriers electrons. So Seebeck coefficient should be negative. But some metals also shows positive value of Seebeck coefficient. So why Seebeck coefficient? Some metals show positive Seebeck coefficient and some metals show negative Seebeck coefficient. What you try to think about, and you send me later the answers. I will try to answer back. That's all. Thank you for your attention.
Yeah, thank you, Dr. Paul, for this nice and informative presentation. Now, we can make this session open to take for any questions from the attendees, so that our speaker can answer those questions. So we already have one question from anonymous attendee. So Dr. Paul, somebody is asking that what is role of Fermi barrier during conduction? Dr. Paul.
I told you that generally in periodic crystal lattice, charge carrier inside any material system, not all charge carriers take part in transport process. Those charge carriers near to the Fermi level only can take part in transport process. For example, sea water. So deep inside the sea, water is calm, silent, but at the surface takes part in waves. So only charge carriers near the Fermi level, you can think in analogy that Fermi level like the surface of sea. So only those charge carriers near the Fermi surface, Fermi level takes part in transport process. So that's why some charge carriers need to cross over the Fermi level to take part in transport process.
Okay, so Dr. Paul, since we can have the next question. Before that, may I request you to just give a brief glimpse about the future prospect? Like we have some aspiring students with us today, the young minds, so they can be interested to know what are the scope for further research, like postdoc or even PhD in your university especially, or in Sweden in general. So if you can guide them in a brief, it will be good for them also.
Okay, so all research with flexible application is becoming interdisciplinary. So it's become more, you need to uh, merge the expertise both from inorganic and organic polymers. So this is an interdisciplinary approach, and it's nice that I'm invited from the Department of Interdisciplinary Research, and it is good also that the department is also offering the polymers course on polymers. This is also good. to move towards the interdisciplinary research. So in thermoelectrics, in last century, people mainly concentrated over bulk application, high power application. But in this century, um, low power application, mainly on-chip cooling, thermal management, electronic system, wearable application, because future revolution, we have come to the stationary electronics, to the portable electronics. Now we are moving to the wearable electronics. And for wearable electronics, energy autonomy is very important for the autonomy of the wearable electronic devices. So how to power them? Um, for example, if any patient is lying on the bed and don't have any solar power, or it, he or she doesn't move, so any um, vibrational power also you can't get. So only source of power is body heat, which never runs out. So thermoelectric can be good source of power generation from body heat. The same power, same food, giving your body the power as well as the device. So it is anticipated there will be huge market for wearable thermoelectric devices in future. And for that, to meet that demand, we need a large number of expertise uh, in interdisciplinary subjects. So regarding material science, if people try to understand the materials in interdisciplinary way, I think their future can be quite prosperous, not only in Sweden, in European world, because future electronics are going to be wearable electronics.
Thank you, Dr. Paul. At the same time, like our institute is offering the MTech in sensor and polymer, as well as MTech in bioinformatics, most importantly MTech in machine learning and data science. I think this all could be very much useful for the further research in the field of material science or like thermoelectric based research. uh, and I have a small question before somebody can ask. Let me see whether anybody, yeah, I have a question uh, from Rafiq Mullah. Most of the theoretical models are somehow related to band energy or band level based. So, whether they can be applied to understand organic or polymeric materials?
Yeah, this is a nice question. Yeah, so far physics is developed based on bands. Organic physics related to organic electronics yet not well investigated. So one organic group in thermoelectrics in Linkoping University, they are pioneer in doing all these studies. So the whole area, a new area is left to discover what happens when band meet with the organic material, inorganic material meet with the organic material. So inorganic material based on homo-lumo, that type of structure. So what happens at the interface? So whole physics need to be developed, yet to be discovered at the interface of organic and inorganic materials. And we need new kind of theoretical development, new kind of physics to understand. So a new area is left or new type of mechanism yet to be discovered to navigate through the interdisciplinary materials.
Okay. So let me see whether anybody is asking. No. So quickly, very quickly, I just want to understand from you. Okay, we have another question. Oh, so Rafiq Molla says thank you to you.
Mm.
Thank you,
Welcome.
Rafiq, for listening. Yeah. So just very quickly, what would be the scope of thermoelectric research or this kind of energy application in the country like India? Is there any scope, or it is far behind the reference or the standard thing in India?
Okay. In India, it can be useful definitely. Mm, you know that recently the concept of autonomous building is developed.
Yes, yes.
Uh, uh, so you need to, for building an off-grid building, you need different source of powers. And you know that sunlight, sunshine, 1 hour of sunshine is sufficient to meet the whole year energy demand. Um, and 40% of sun energy is wasted at heat. So walls of our homes get heated. So thermoelectric device can be used to generate power from that heat. And you know that we are facing now crisis with coronavirus. So we are locked down inside the home. If central system is collapsed, that no electricity, no water comes, then what happens to us? So that's why to avoid the civil crisis, every building need to be autonomous. So for that, thermoelectric can be very promising in this direction to develop self-powered building. And definitely, I told you that um, that thermal management of electronic devices is very important, and thermoelectric coolers can be very useful. And what other advantage of thermoelectric device that it offers maintaining free operation for long time. So this is helpful for our country also. So we need proper measure how to make the roadmap in which area it can be implemented. In some cases, we need hybrid power sources. You know that due to the there is a treaty in Paris Convention, we need to reduce carbon. So we need all different type of hybrid power sources. So thermoelectric is one important. So it's definitely important for our country. So I got one question. As solar cell produce heat,
Yes, yes, please.
as solar cell produce heat, so how thermoelectric materials can be useful in solar cell? Uh, there are some groups. They are trying to build hybrid solar cells, combining photovoltaic and thermoelectrics together. What happens in solar cell? We use the visible range of spectrum to generate power, but infrared range is left out. So if photovoltaic and thermoelectric is hybridized, the efficiency of the device, hybrid device, can be enhanced because thermoelectric device can convert that left out heat that solar cell generates heat, as someone mentioned, that can be used to generate power by using thermoelectric device.
So, Dr. Paul, I have a I just want to know whether it is my question. We can see that in our maybe it seems very far-fetched idea. So when we are using laptop or desktop, they are getting very much heated sometimes. So is there any way to utilize this kind of heat difference or generated heat to run the machine or something like that?
Yeah, what happens? You know that according to thermodynamics law, no machine cannot be 100% efficient. So definitely all machine generates heat. So computer also generates heat. So thermoelectric device can be used to convert that wasted heat into electrical power, and that can be used to charge mobiles or other things. For example, microelectronic devices like sensors doesn't need much power. It, the wasted heat from computer and little hot surface is sufficient to power a sensor network. So thermoelectric is sufficient. So from that heat, milliwatt or microwatt, ECG, EEG, all those devices can also be run. So as the power demand of electronic devices goes going down, thermoelectric micro device becoming more valuable day by day. And also efficiency of human body is 15 to 30% about. So most energy also wasted as heat. So there is always, you will get some heat. So thermoelectric is always important. So in previous century, bulk thermoelectrics mainly was concentration. So for high power application. So for high power applications, other sources are a bit more efficient, but for micro device, micro scale application, thermoelectrics doesn't have much competitors in some specific application.
Okay, thank you, Dr. Paul. So we have some more questions here. So one more anonymous attendee asked that can mobiles or smartwatches be charged from body energy?
Yeah, of course, that I showed already in a slide. Uh, that some glass watch is sufficient to can be charged from body heat. And there was already one company that launched watch powered by thermoelectric device long ago. It was not so popular because thermoelectric device was big, but with micro thermoelectric device, uh, it's possible. Not only mobile, many wearable devices. So you can when you see some Hollywood movie that Mission Impossible, that someone is wearing spect with computers integrated with that. So that type of system, wearable computers, can easily be uh, powered by thermoelectric device from body heat.
So Dr. Paul, another attendee, Abhishek Paul, has asked another question that what will be the role of graphene in thermoelectric? Yes.
Yeah, gra- graphene has become like holy grail. So some people investigated on graphene, graphene oxides. So problem with graphene, it has high thermal conductivity in one plane direction. But if proper engineering is done, it can give high output power. So for low power application, thermal conductivity is not much of concern. Graphene can be useful for flexible thermoelectric application, but it needs rigorous materials engineering to tune the thermoelectric performance.
Yeah, Dr. Paul. Yes. The next question is from Dr. Sumanta Kumar Koron. He has asked that can it be useful for body monitoring, this kind of wearable thermoelectrics, and is there any present commercial application for this?
Um, that type of application yet not commercialized, that is powered by thermoelectric. There are some prototypes. Body monitoring is really important area because it doesn't need much energy. So some big companies like Google, Apple, Microsoft has already stepped into that body monitoring devices that can be easily powered by wearable thermoelectrics. So I expect that some commercialization, wide commercialization near future.
Okay. So the next question is from Narasimha Rao Kicham Seti. Maybe I spelled it wrong, but sorry for that. He asked that, is it possible to store the electric energy which is drawn from the thermoelectric device by using batteries or supercapacitor?
Yeah, actually, purpose of thermoelectrics, one way is to replace battery, because you know that battery has huge environmental impact, and it needs periodic recharging, and it has huge environmental impact at disposal. So I don't think battery would be good to store the energy, but definitely supercapacitor can be combined with. And for wearable application, actually we need certain storage to regulate the um, operation in a regular manner. So this is important. When we think about real application, we have several steps. One is power generator, other is storage, then to the electronic device. So it's really important. But battery is not good option for environmental impact. So we always focus, raise question about battery. That's why.
Yeah. So thank you, Dr. Paul. And the next question is asked by Dr. Pandyasaran Veluswamy. He is asking, in Japan, 1993, Seiko company released a watch by body heat. It can charges by body heat. Uh, and it is whether, I don't know whether it is a question or a suggestion
Yeah,
or
yeah, yeah.
comment. Yeah.
He mentioned that. Actually, I think I mentioned one company long before did that. So
Yes, yes.
he is pointing on that. Actually, that company I was mentioning about.
So do you want to give up any comment or something like that? Or otherwise we can move to the next question. Yeah. Yeah, he said that yes, you mentioned it earlier. Yes. So
Yeah,
I think
thank
it
you,
is being
doctor,
sorted.
for mentioning that. I couldn't pronounce the name of
Yes.
the company, not.
Right, right. So he reminds you the name of the company. So I think all the questions have been answered, and if there is no further question, so that we can wrap it up here. And once again, that thank you, Dr. Paul, for your nice and
You.
informative interaction and the presentation. And you have managed your busy schedule for us. And I'm sure that in future we will love to have you again for this kind of presentation. So there might be another question. No
No,
question,
it's
but
a thank you message,
somebody's, yeah,
and thank you
some
to
message.
all
Yeah.
for giving me the opportunity to share my experience and little knowledge.
Yes, yes. On behalf
And
of our family, JISIASR family, and on behalf of our director and faculty, all the faculty members, I would like to convey our sincere thanks for your time and presentation. Yeah, please, Dr. Paul, you can say.
okay, thank you very much to all,
Yeah.
and nice questions I encountered, and that I expected. Mm. But I couldn't go deep inside the thermoelectrics physics because it was broad. It was for broad audience. I gave an overview. So anyone, those who want to do research in this direction, there are some references you can follow that will guide you in certain way. That I expect that can be helpful.
Okay, so here we can end today's webinar. Thank you, Dr. Paul. Once again, have a nice day and stay safe in there. all the attendees on behalf of our institute. So I would like to convey my thanks and sincere regards for your time and for participation. So our next webinar will be tomorrow, and you can see our Facebook page for details, and hope to see you all again in the next series of webinars. Thank you. So here we will leave, and thank you, Dr. Paul. Thank you,
Thank
everyone.
you.
Okay, bye-bye. Bye.
Bye.
Yes.